This is what you get. This is what you get when you mess with love. Karma always. I've given all I can, not enough. I've given all I can, but we're still on the payroll. This is what you get. This is what you get. This is what you get when you mess with love.
Time for a few more.
The green plastic watering can for a fake Chinese rubber band and a fake plastic gun. she bought from a rubber man in a town full of rubber bands to get rid of the sand. The world's around, the world's around, the world's around, the world's around. She lives with a broken heart, a crackpot's dying man who just crumbles and burns. Used to do surgery because of the answers, the gravity the world's around. The world's around. Was new. It was new. It was new. It was new. If I could be who you wanted, if I could be who you wanted all the time, all the time.
Fake Plastic Trees by Radiohead. We're out of time. We're out of time. So a few questions have come up. Ben, if you want to give us that question. Oh, there it is. Very good. Odd and even functions, you are responsible for that. Differentials we have not discussed, so they will not appear on the final exam. Somebody was asking the difference between linear approximations and differentials. Differentials, right, in the dy dx notation, dy or dx themselves can be studied, and these can be viewed as objects in their own right. So differentials, these dy alone or dx, those are differentials. We did not discuss them, so they're not going to appear. Somebody was asking about 3.7, rates of change in the natural and social sciences. I think we did a few examples from that section, namely as it relates to velocity and acceleration. We're not going to go into specifics related to interest or population growth or radioactive decay. We didn't do that. We're not going to do that. That's not going to come up on the final. What is the purpose of linear approximation? Is it only useful when you don't have a calculator? Well, that's certainly one approach, right? It's a way to approximate your function. It's a way to simplify, right? I mean, not only if we don't have a calculator, but what if you don't actually have the function itself? What if you only have the function at a point and its derivative at a point? This still allows you to approximate. There are no decay problems on the final exam. The final exam is 3 hours, yes. So Ben was, do we need to know a formula for midpoint and distance? Well, certainly distance. Midpoint, I mean, you should know the point between two, yeah. So Ben was asking a question. Yeah, okay, there it is. That seems very similar to the question we had on the midterm. I think the question, no orthogonal trajectories, no. I think Ben had mentioned that the function was continuous and differentiable as well. Formula for volume and area of cones, cylinders, and equilateral triangles. Certainly cylinders for sure, and triangles, yes. Yeah. I mean, you don't need to know the formula, but I mean, you should be able to work it out in a moment. So if you plug in 0 for x, this is f of 2 and f of 2, and they're both 0. So this has the form 0 over 0. A quick L'Hopital's rule does the trick. And, you know, I mean, I was looking at midterms again over the weekend, and a lot of people don't carry the limit sign around. We were generous in the marking. If you don't carry the limit sign around, everything is wrong, right? So don't do that. F prime of, when you plug 0 in, assuming the derivative is continuous, and I would hope that that's what was mentioned. in the question. This is going to be f primed of 2 times 3. And f prime of 2 times 5, 6, 7, 8. 8 times 7 is 56. Is there a way to evaluate that limit without L'Hopital's rule, like we did on the midterm? And I think there is. I think you can do that. Probably with some more difficulty, but I suspect. I mean, what I'm going to invite you to do is just do one of them. So just do this one over that, and try to do it without L'Hopital's rule. Well, I mean, you want to recognize this as the derivative, as f primed of 2 somehow. Somehow. So you want try it. Yes. No. This is not. Somebody was asking if this is the final section. This is not the final section. We're finishing curve sketching today. Moving on to optimization, probably on Wednesday, and antiderivatives. So finishing the course essentially on Friday. That's the hope. Leaving us Monday for some sort of review. Look, never have I not written limit. It's 3 letters. You need to write limit. Write the limit always, always, always. 7 is f prime of 2. When you plug 0 in, you get f prime of 2, which is 7. All right, let's try this. This is not the actual question in the book. In the book, they don't have the absolute value. Now, while I did not tackle this question earlier, meaning I didn't work it out, I decided to throw in absolute values. I think we're going to be fine. I think the whole question is going to be fine with absolute values, so let's try it. First thing you want to do is discuss the domain. What is the domain of this function? There should be tutorials on Monday next week. It's Monday is a regular day. Everything except 0, thank you. Zero's an issue, right? Because you know ln is not defined at 0. And x and y intersect. If x is 0, slash means except. So all real numbers except 0. Will there be something to the derivative of x to the power of x on the exam? Why not? You know how to tackle that. Right, so x is not 0. So no x intercepts. No y intercepts. If y is 0, x cannot be 0. So we need ln of x to be 0. And that happens when x is plus or minus 1. Thank you, Paul. Why are negative numbers within the domain? Well, notice I have absolute value here. So it's not an issue. It's not an issue. The book did not have absolute values. So I changed it slightly. I don't think it's going to be an issue for us. I don't think working with the absolute value is going to change anything, meaning that this is the question the book should have had. All right, we're moving on to the first derivative, dy dx. You know what to do. This is a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. And you know the derivative of is 0 divided by x. Where are we talking about there, Sophia? How come you just get rid of x? Right, so 0 divided by x. You know x cannot be 0. So 0 divided by any non-zero number is 0. Con is asking, do we not have to find horizontal and vertical asymptotes? I usually do that at the end. Where the absolute value make the function not differentiable. It might make the function not differentiable at 0. Might, I say might, but 0 is not even in the domain. So that's not an issue. Jade is asking if we need to test if the function is odd or even, and it's a good idea to do so. I mean, you can again save that until the end, but I'm sure you've recognized that the function is indeed odd. Is there a difference between the derivative of x compared to the derivative of absolute value of x? There is. There is. Absolutely. And somebody's asking, why is it not 1 over absolute value of x? We did that way back in the day when we introduced the derivative of ln x. We saw that the derivative of ln of absolute value of x was still 1 over x, right? Ln of absolute value of x decomposes as ln x if x is bigger than 0, and ln of negative x if x is less than 0. Both of these have derivative 1 over x. Should not, people, it should not be 1 over absolute value of x. Derivative of ln x is 1 over x. The derivative of ln of negative x is 1 over negative x times the derivative of the inside. So the whole thing is still 1 over x. So whether you use this one or that one, the derivative is always 1 over x. There it is. Convinced? Let's factor out. So this will cancel with that. Let's factor out a ln of absolute value of x, leaving you with ln of absolute value of x plus 2. Well, Zuhair, I'm going to let you work that out. This is not a difficult question. What you want to do with absolute values is get rid of them. Get rid of the absolute values like we did for the ln absolute value of x. All right. Critical points, where the derivative is 0 or where the derivative does not exist. Derivative does not exist at 0, but that's not in the domain. So the only critical points are where the derivative is going to be 0, and you've got a product equal to 0, so you need one of the factors to be 0. Ln of absolute value of x is 0, or this is equal to 0 when x is plus or minus 1, and this is equal to 0 when x is, you know what it is. Plus or minus e to the negative 2, is that correct? Thank you. This is something like 1/4, 1/5. So minus 1 minus e to the negative 2. 0, which is not in your domain. E to the negative 2. And 1. All right. For large negative values, this is going to be a large positive. This is going to be a large positive. Everything is positive. Your function is increasing. If you take something very close to negative 1, let's say right here, this is going to be close to 0, but less than 0, right? So you're taking a number less than negative 1. So this is going to be negative. This is going to be close to 0. So this is going to be positive. So negative, positive, the whole thing is negative. As Colin is asking if we can do a different first derivative chart. Look, as long as the information is there, we're good to go. Why are we including the x-intercepts on the first derivative? We are not. We are not. The x-intercepts are not important. It's the critical points that are important. And it turns out that the critical points are actually the x-intercepts. Coincidence. If you take a value very close to 0, this is going to be a large negative. This is going to be a large negative. So the product is going to be positive. Same thing here. If you take a value very close to 0, large negative, so the whole thing is going to be positive again. If you take something close to 1, but just less than 1, this is going to be close to 0, so that's going to be close to 2. This is going to be a negative number. So negative. And finally, if you take a large positive, there's going to be positive, positive, everything is positive. There it is. What is happening at negative 1? We have a local max. Local min occurring at e to the negative 2. Nothing's happening at 0, apparently. Local max here. And a local min over here. Can we explain how ln x is negative? Well, you know the graph of ln x. Right? And you know that it's 0 at 1. So if you take something less than 0, if you take something less than 1, it has to be close to 0, but negative. Miriam is is asking how a number less than -1 makes f positive. Take a very large negative number. The absolute value makes it a very large positive. And for large values of x, the function is very large. So this is going to be positive. This is going to be a large positive number. This is going to be a large positive number. Plus 2 is going to be an even larger positive. Positive times positive is positive. Right? I mean, 0 is not even in the domain. So, of course, nothing happens at 0. Very nice. And then Colin was asking, why is 0 in the first derivative chart? Since it's not a critical point, correct? But it's not in the domain, so it has to be included in your first and second derivative charts. Exactly that. Here the behavior does not change. So nothing, well, yeah, behavior did not change at 0, but we saw that in some instances it does. What does writing with plus and minus 3 times mean? Means nothing. Just means the derivative is positive. So your function is increasing. I've taken the habit of writing it 3 times. 1 is sufficient. As long as the marker understands what's going on there. How do we compare the magnitude of 1 and e to the -2? Well, e is 2.71 something, so it's a number between 2 and 3. So 1 over e is going to be between 1/2 and 1/3. And when you square it, it's going to be between 1/4 and 1 over 9. That was it. How does taking a really small x value merit a positive y value? Well, you know the behavior of ln x. If x is very close to 0, ln is going to be a very large negative number. Large negative. Large negative plus 2 is still a large negative. Negative, negative, positive. Second derivative. Is that right? Possible points of inflection? Where the derivative does not exist, where the second derivative does not exist, that would be 0 and 0, but those are not in the domain. Otherwise, where this is 0, and this is 0 at plus or minus, how did you find the interval between -1 and e to the -2? And negative e to the -2. I said I was going to take a number very close to -1 here. Without actually plugging in, if I take a number very close to -1, ln is going to be very close to ln of 1, because ln is continuous. Ln of 1 is 0. So this part is going to be positive. If I take a number less than -1, the absolute value is going to be less than 1. And ln of a number less than 1 is going to be negative. So negative positive, the whole thing is negative. Raycon is questioning the notation here. And what does this represent? I mean, the notation is very nice. This is Leibniz notation, right? What are we doing? We're differentiating this. We are differentiating with respect to x the first derivative. So we have two d's. So the d squared, and you have two dx's. So dx squared, if you will. Nobody puts brackets, but that's the idea. How much time would we be given for a question like this on the exam? Because you're thinking to yourself, we've already spent 20 minutes, we haven't even started graphing. But, I mean, you're not going to be answering your neighbor's questions. "10 minutes, 15 minutes should be more than enough." Well, the idea is that the bottom should really be this, right? But again, it's just notation. So this is the good notation. Well, it's plus or minus because of the absolute value, right? We have ln of absolute value of x is equal to -1. So you take the exponential of both sides, and you get absolute value of x is e to the -1. So x is plus or minus. All right. Second derivative, let's do the second derivative chart. I'll let you do the second derivative chart. I'll be back in a moment. Try that. All right, sorry about that. Little emergency. We're back. How did we get this? I mean, I just erased it. It was right here. Exactly as Connor is suggesting there. All right. So possible points of inflection: negative e to the negative 1, 0, and e to the negative 1. So if we take a large negative number, this is going to be negative. Large negative in absolute value is going to be large positive. Log large positive is a large positive. So this is going to be positive. Positive negative makes everything negative. Concave down. If we take a number close to 0, but less than 0, this is still negative. This is going to be a large negative number. Plus 1 is large negative, so negative negative is positive. Concave up. Same thing here. If you take a number close to 0, but positive, this is going to be positive. This is going to be a large negative number. So positive negative is negative. And finally, if you take a large positive number, this is positive, everything is positive. What is happening here? We have a point of inflection. Point of inflection here as well. Remembering that 0 is not in the domain. So nothing happening here. 0 is not a point of inflection because it's not in the domain. All right, we're almost ready to go. We want to know where to start, where to end. So we need limit as x goes to negative infinity. I think this was our function here. As x goes to negative infinity, this is going to go to positive infinity. Log of infinity is infinity times, well, infinity squared is infinity times negative infinity. The whole thing is easily seen to be negative infinity. Why are we interested in the behavior around 0? Well, you're thinking to yourself, why am I choosing values close to 0? Because I don't have a calculator and I don't want to worry about what this is. A simple argument by saying take a point close to 0 and you're good to go. Even though it's not a point of inflection, doesn't the function look like a point of inflection at 0? Well, we don't know the behavior at 0 yet, right? And we're going to have to work that out because 0 is not in the domain, so we want to know what happens close to 0. So we're going to evaluate the limit, but we have not done that yet. As x goes to infinity, this is infinity, this is infinity, the whole thing is infinity. Now, what is happening near 0? What is happening near 0? It's a good question. We don't know. Right? 0 is not in the domain. So what's going on near 0? In other words, what is this limit? And first of all, as x goes to 0, ln of 0 is negative infinity. So this has the form 0 times infinity. Right, Sophia? Thank you. Right, it has the form 0 times infinity, an indeterminate form. And so we're going to rewrite this as Sophia suggested. In this form. And now we have infinity over infinity. Why does taking a very small x give us a negative y? Where are you? I'm not sure what you're talking about, Andrew. Are you talking about here? So now this has the form infinity over infinity. We can apply L'Hopital's rule. Derivative of the top. Derivative of the bottom. Melanie, ln of absolute value of x all squared does not go to negative infinity, right? I mean, it's going to go to positive infinity. It's the ln itself that goes to negative infinity because ln of 0 is negative infinity. You know the graph of ln. The leftmost side, this one here, leftmost side of the second derivative chart, you're taking a large negative number. This is negative. And this is positive. So negative, positive. When you add 1, you still get something positive. And as Sophia suggests, even if the infinities were of different signs, you could still use L'Hopital's rule. Let's cancel one of these. And you still have an infinity over infinity. Very similar to what we had before, right? So derivative of the numerator, derivative of the denominator, this becomes positive. Andrew is asking why is ln? Why is this positive? I'm saying take a very large negative value. Take a very large negative x. When you take the absolute value, it's a very large positive. And ln goes to infinity. So it's going to be positive eventually. Doesn't the limit as x goes to 0 not exist? No, in fact, it's going to exist, right? I mean, I think it's easy to see that this limit is 0. Well, let me not skip a step here. And this is really 2x, whose limit is 0. And you can see that nowhere did we use the fact that you're taking the limit from the left. If you do the limit from the right, you'll get the same thing. Well, the denominator was 1 over x, but when you differentiate, we're applying L'Hopital's rule again, right? So we essentially have a removable discontinuity at 0. Notice, as somebody pointed out originally, if f of x is x ln of absolute value of x all squared, f of negative x is negative x ln of negative absolute value of x, which is negative x ln of absolute value of x all squared, which is negative f of x. Two over infinity if you want, sure. But if you flip that back up, you get 2x, which is 0. So what are we saying here? F is odd. Thank you. So now let's put everything together and graph. Let's try to fit it in here. We're graphing from left to right. So for leftmost values of x, when x approaches negative infinity, your function is going to negative infinity. Erase some stuff here. So we'll be starting somewhere here. How many points is the graphing question on the exam worth? Well, I don't know that we have a graphing question, but if we did, it would be worth a lot, right? Because there's a lot of work to be done here. And Zoe suggests that it is not a removable discontinuity. And you're right. You're right, right? There's that subtlety that 0 is not in the domain, so we can't even talk about continuity there, but it's almost a removable discontinuity. So we're starting at negative infinity. You better be increasing. And you are, right? So your work is consistent here. Caesar is asking what happened to ln of absolute value of x. Well, you tell me. I claim we differentiated to get from here to there. Right? We applied L'Hopital's rule. So we're starting here, we're increasing, concave down all the way to -1. I've rubbed off the x and y intercepts here, but I think we did not have any y intercepts, but we had x intercepts at -1 and 1. So increasing, concave down all the way to -1. And then you are decreasing, still concave down all the way to -1 over e. at which point you are still decreasing, but now concave up all the way to negative 1 over e squared. Sorry, negative 1 over e is out there. Negative 1 over e is here. And then all the way to negative 1 over e squared. So decreasing, concave up all the way to there. And then we are increasing, concave up all the way to 0. Where's the 0 taking us? 0 is taking us to 0. And then after 0, you're increasing, concave down all the way to 1 over e squared. And then you're decreasing, still concave down all the way to 1 over e. At which point you're still decreasing, but now concave up all the way to 1. And you'll recall that 1, we had a x-intercept. And then you're increasing, concave up forever. And where's the forever taking us? All the way to infinity. And notice, right? I mean, I've rubbed it off now, but your function was odd, and this is, you have this nice symmetry. You have this nice symmetry. We have a local max here with a horizontal tangent line, a local min right here with a horizontal tangent line as well. A kind of removable discontinuity, if you will. Let's not call it that, but and we have a local min here as well. It would be nice to work out these y values. Do we want to? Right, this is the graph of x ln absolute value of x all squared. So at e to the negative 2, this is negative 2 squared is 4. So this is 4 over e squared. And of course, this is going to be its negative 4 over e squared. And you have points of inflection right here. It's nice to work them out also. This is negative 1 squared is 1. So this is going to be negative 1 over e. And over here, a point of inflection as well at 1 over e. Very nice. Very nice graph. Since it is odd, as Eddie suggests, we could just reflect this across the origin. That's right. Across a line y equals negative x. If there's only an open point at 0, does this always mean that 0 is not in the domain? Well, I mean, unless you had a closed point somewhere else, right, on that vertical line. Somebody suggests if you make a small mistake in the beginning, everything else is wrong. Do you get some sort of part marks? I would hope that you would notice an inconsistency in your work. Right? You would notice probably some inconsistency somewhere along the way, And then you could go back and figure out where the mistake was. This is such a nice question that I would have put it on the final exam if it had been an odd numbered exercise. How do you know in general that a function has symmetry? Well, myself, I would have graphed it first, and then I would have looked and said, maybe there is some symmetry here. Did I have an odd function to begin with? And then I would have checked. Juliet suggests to work out the point and say it's a global. Well, no, I wouldn't say global, right? It's not a global minimum because your function goes off to negative infinity here. It doesn't look like a reflection, but it really is. I view it more as a reflection about the x and then about the y. It's easier for me to view it that way, so I'll encourage you to consider that. I know we're out of time, but I had to take some time off to deal with something. So let's do one more example. And before we do that, let me introduce a definition. I mean, we had the limit going to infinity here of your function. Limit as x goes to infinity, or limit as x goes to negative infinity. We've discussed the idea of horizontal asymptotes, right? If that limit behaves like a straight line. We can extend that notion and say that functions f and g if the limit as x goes to infinity of f of x minus g of x is 0. Right? If the limit of f of x minus g of x is 0, then we can say that the functions f and g behave in the same way as x goes to infinity. Right? I mean, the particular example is if g of x is a constant, then g of x is said to be a horizontal asymptote. And x goes to negative infinity similarly. And the point is that if g is a simple function, something that you know the graph of, right, like a straight line, or perhaps, a straight horizontal line, or perhaps just any straight line, or an x squared, or an x cubed, and so on, you can use that to your advantage in helping you graph the function, right? Because it's all about graphing functions. So if you can bring it back down to simpler functions, you're good to go. definition. Y equals mx plus b is said to be an oblique asymptote of f of x if limit as x goes to infinity of your function minus that straight line is equal to 0. Or Con is asking how did it help us graph knowing the function was odd or even. Well, Eddie suggested you could have just graphed half of it, the positive half for x bigger than 0, and the negative half would have been the reflection above the line y equals negative x, or above the x-axis and then the y. So knowing just half of it, you could have figured out the other half. And is it necessary that we should check whether this function is odd or even? You should check. Would it have been easier to plug in your critical points into the second derivative test to find intervals of increase and decrease in this case? You do not get increase and decrease from the second derivative, right? So that doesn't work. Right, so in the particular case that G is a straight line, these are known as oblique asymptotes. And that's fine. Con is suggesting he would rather do all the work, and of course you would, so would I. But once you've done it, and you look at the graph and you're thinking to yourself, oh, there seems to be some symmetry, why don't I prove it? Showing that the function is odd or even is what you want to do. Right, so here we're defining the idea of oblique asymptotes. And let's illustrate with an example. Not page 74, but number 74, we are asked to sketch All right, so let's sketch this. First question, what is the domain? Domain? All real numbers. X and Y intersects. If X is 0, well, if X is 0, Y is easily seen to be 1 plus E. And if Y is 0, who knows? Right? If Y is 0, it's not immediately clear how to solve for X. Let's postpone. Let's not worry about it. And let's move on to the first derivative. Y prime minus Y to the 1 plus x over 3 times the derivative of the inside. Critical points. Clearly, the derivative is always defined, so critical points are going to be where this is equal to 0. So minus 1 plus 1/3 is equal to 0. Bring the 1 over, and then the 3 e to the 1 plus x over 3 is equal to 3. Take ln of both sides. 1 plus x over 3 is ln 3. So x is easily seen to be 3 ln 3 minus 3. Is that correct? Does everybody have that? Let's draw a first derivative chart. Thank you, Eddie. Let's draw a first derivative chart. Where is this situated? Notice that 3 is bigger than e, and ln of e is 1. So if this was an e, the whole thing would be 0, and ln is an increasing function, so this is bigger than 0. And this is in fact your only, well, so I mean we didn't even need to notice that it was bigger than 0. All we had to do was take a very large positive number. And if you take a large positive number, this is going to be a large positive. So this whole thing is going to be a large positive. Minus 1 is still going to be a large positive. And if you take a large negative value of x, this is going to be negative infinity. And e to the negative infinity is 0. So the whole thing is going to be negative. Which means that you have an absolute minimum occurring at that value. Move on to the second derivative. And that is easily seen to be 1 over 9 e to the 1 plus x over 3. And exponentials are never 0, so you have no possible points of inflection. A second derivative chart. If you plug in any value, the exponential is always bigger than 0, so the whole thing is always positive. Your function is always concave up. Let's figure out where we start and where we end. What is the limit as x goes to negative infinity? And as x goes to negative infinity, this goes to negative infinity. E to the negative infinity is 0. This goes to negative infinity, so minus minus is positive infinity. The whole thing is easily seen to be infinity. And now here's the question. When we have a limit of infinity on one or both sides the question now arises, do we have an oblique asymptote? Does this function behave like a straight line for large negative values of x? That's the question. Is there a straight line, y equals mx plus b, for which this limit minus the straight line is equal to 0? Can we tell without graphing it? Well, that's the thing. The answer is yes. We want to tell without graphing it so that we can graph better. We want to figure out the oblique asymptote so that instead of graphing this complicated function, we're going to say that it, well, Eddie has given us the answer. We're going to say that for large negative values, your function is going to behave very close to this. And this we know the graph of. So it's going to help us graph. And if we, so how did Eddie come up with that answer? I think he just read it off, but let's do it systematically. If you expand and group, this is going to be 1 minus b plus x times minus 1 minus m. So I'm grouping the constants together, right? Expand this and group the constants and the stuff in x. So you have minus x minus mx, or x times minus 1 minus m. And finally, the exponential business. And we want this limit to be 0. And as Sashir points out, this business goes to 0. So you can disregard that. Problem solved. If this is not 0, then as x goes to negative infinity, this part's going to go to negative infinity. So the whole thing will not be 0. So in order for this to be 0, we need minus 1 minus m to be 0. In other words, y is 1 minus x positive infinity. You know why. Just plug it in. So we need m to be negative 1. And if m is negative 1, this whole thing disappears. And then the limit is just 1 minus b. But that should be 0 as well. So we need b to be 1, giving us exactly the answer Eddie had suggested. Absolutely. Absolutely, Bree. In other words, what? Y equals minus x plus 1 is an oblique asymptote. As x goes to negative infinity. The e part goes to 0 because it's e to the negative infinity, which is 0. Well, it's e to the negative infinity. You know what e to the negative infinity is. Now, what about The limit as x goes to infinity. Let me point out that we had, if x is 0, y is equal to 1 plus e. Y is b0. This goes to 0. If m is -1, this thing has disappeared, so that's 0 as well. So the limit is just 1 minus b, but 1 minus b has to be 0. So b has to be 1. And as Sophia suggests, if it's not possible to solve for m and b, then that means there are no oblique asymptotes. How did you know that this function would have an oblique asymptote? I did not. We did not know. We asked the question, do we have an oblique asymptote? So when do you search for an oblique asymptote is perhaps your question. And you search for an oblique asymptote when the limit is plus or minus infinity. If you have an infinity as the limit, then you ask the question, is there an oblique asymptote? We searched for it, we found it. It doesn't mean there is one. And if we do the same, well, I mean, first, let's figure out this limit. As x goes to infinity, what is the limit? This goes to infinity. This goes to infinity. So we have infinity minus infinity. Boy, if b is 1, there's no bx, right? B is bmx plus b. B is not multiplying x. Right, so infinity minus infinity, you know what to do. Right, this is an indeterminate form. How are you going to answer that question? Exactly, Melanie, mx plus b, right? How do we answer this question? Exactly as pointed out here, only when the limit is plus or minus infinity do you search for oblique asymptotes. Not any limit. Limit as x goes to infinity or limit as x goes to negative infinity. It's the behavior of your function for large positive values or large negative values. Here we're saying for large negative values, your function is behaving like this straight line. Factor out an x, or I would have suggested factor out the exponential. Because that is the dominant term. If you factor out the exponential, what are you left with? 1 minus x over the exponential plus 1. And as x goes to infinity, this part goes to infinity, granted. Let's answer the question, what is happening here? This has the form infinity over infinity. So a quick L'Hopital's rule gives you minus 1 over e to the 1 plus x over 3 times the derivative of the inside. A quick L'Hopital's rule gives you tell me, You see what it is? This limit is 0. So this stuff in the brackets here goes to 0. So the whole bracket goes to 1. This goes to infinity. So the whole thing is infinity. Absolutely. So now, question arises once again, is there an oblique asymptote? Right? Same question, is there an oblique asymptote for which not limit as x goes to negative infinity now, but positive? Right, so same question, but on the other side of the graph. And if we do the same, right, if you group as you did before, 1 minus b minus x times 1 plus m, if you will, plus the exponential. And if you're forcing this to be 0, Melanie is asking, how's 0 times infinity equal to infinity? It was never 0 times infinity. This goes to 0, but you still have a plus 1 here. As Connor suggests, you had 0 plus 1 times infinity. And if you do the same, if you factor out the exponential, leaving you with this business over the exponential. Right, you see how it's essentially the same as what we had before. It is hard for us to realize that there is an oblique asymptote because there are also many functions that have negative infinity when limit goes to infinity and does not exist an oblique asymptote. You're right. You're absolutely right. Luckily, there's a systematic way for us to work it out. Subtract mx plus b and force the limit to be 0. If you're able to solve, you're good to go. Here we pull out an exponential. So exactly the same work as we did in here. And now do you see that regardless of what m and b actually are, this thing always goes to 0. This goes to 0 regardless of what m and b actually are. So the whole bracket is going to go to 1, and this goes to infinity. And now we're in trouble. That limit is actually infinity. It's never 0. Right? The fact that this goes to 0 is the same work as here. One L'Hopital's rule does it. So this limit is always infinity. It's never 0. You should check. You should always check the oblique. If you have a limit that is infinity or negative infinity. Yes. But here, no oblique asymptotes on the other side. let's finish that up quickly. Let's graph it here. We had an oblique asymptote as x goes to negative infinity. So let's graph the line y equals negative x plus 1. The limit as x goes to negative infinity was negative infinity, so we're starting at negative infinity. Notice, right, that this is the line you had here. This was how Eddie was able to give us the answer immediately. It's this line plus this insignificant business when x is negative infinity. When x is a very large negative number, this is very close to 0. Always positive, but very close to 0. So the function is always a little bit larger than this. You're starting above this line. You were starting at negative at positive infinity. You better be decreasing, and you are decreasing, concave up all the way to this value. I don't know what that value is. Maybe we should figure out what that value is. If f of x is 1 minus x plus e to the 1 plus x over 3, f of 3 log 3 minus 1, like this, and this is e to the 1 plus log 3 minus 1. These cancel out. This is just 3. So this becomes 3. And so this is plus 3, that's 6. So that's 7 minus 3 log 3, I think. Okay. And it's easy to see that this is going to be positive, right? Because 3 is less than e squared. And when you plug in e squared, you get positive 1. So this is going to be bigger than 1. So whatever. Decreasing until this, which we had argued before was bigger than 1. I mean bigger than 0. So you're already here. So whatever happens. With an y-intercept, if x is 0, this is 1 plus c. And this business is really 7 minus 3 log 3. And then you are increasing, still concave up, all the way to infinity, and then there's no oblique asymptote there. So we have an absolute minimum occurring there. Why do we start above the asymptote, right? Here was your asymptote, and then you're adding something positive. For large negative values of x, this is going to be positive. So it's your line plus something. You're just above. There it is. How are we doing? Right, again, the oblique asymptote is just the behavior for large negative values. That's all we're saying. What was the 7 minus 3 ln 3? It was the value, the y value at this point. So this is the point, 3 ln 3 minus 3 and 7 minus 3 ln 3. It's a lot, I get it. Everything's coming together. So it's nice in that sense. How did you know 7 minus 3 ln 3 was bigger than 1? Three is less than e squared, right? Because this is 2.7 something. So this is going to be bigger than 4. And ln of 3. So ln 3 is less than ln of e squared, which is 2. And then if you multiply the whole thing by negative and add a 7 and multiply by 3, and add a 7, well, if there is an oblique asymptote and you don't solve for it, and the question asks you to find the asymptotes, including oblique asymptotes, you would lose some marks. In the textbook, they had graphing questions with trig. Would you restrict the domain in attending these problems? Probably not. If they do restrict, then that's fine. But in some cases, you can do it without restricting. Jonas is suggesting there are lots of opportunities to make small mistakes and get everything wrong, right? But there are these checks along the way. Is your work making sense? Does your work contradict itself, or is it consistent? If something seems to be contradicting itself, then you know a mistake has been made. All right, practice this. On Wednesday, we will tackle optimization. You should do graphs with trig functions as well, absolutely. Everything is fair game if it's an odd numbered question in the book. Will we be drawing on graphing paper in the exam? You should not expect to have graphing paper. Right, just a rough graph. It doesn't have to be to scale. Well, like I said, the example we did before, the x ln absolute value of x all squared, that would be a very nice final exam question. All right, folks. Thank you all for coming. And I will see you guys on Wednesday.